Now we come to one of the more complicated features of Numipulator. Now nearly every game, puzzle or any other type of app needs to remember some values from one cycle to the next. In games you'll need to remember the positions of counters maybe, or cards in a hand, or the positions of objects, and probably remember the score as well. Now this is normally referred to as state. What state is the game in? Numipulator has special boxes called memory boxes, either memory numbers or memory lists, that's in row Y and Z, that allow individual numbers or lists of numbers to be remembered for the next cycle. Let's start off with the simplest one, that's memory number, and suppose we want to program a simple incrementer so that we have a number that increases by 1 each cycle. First, let's clear the program and assume that it is the value of y1 that we wish to see increase in value each cycle. As with the other boxes, the bottom field will contain the output value, and this is what y1 refers to. So if we have the value y1 and we wish to add 1 to it, we can go to a1 and we can say let's add 1 to this. So we take y1, we add 1, so that's going to be y1 plus 1, and let's go back to y1 and look here and say therefore that the next value that we want is going to be a1. The idea is that during a cycle the value for a1 is calculated, and the result for this goes into the mem field just underneath, and this is the specification for y1 in the next cycle. So the mem field effectively remembers a value from this cycle for use in the next cycle. Now you might notice one issue with this setup. In the first cycle there will be no specification in mem to calculate the first value of y1. So this is where the top field init comes in. We put the specification to go in to mem in the first cycle in here. So let's say we want to start off at 1, and now we press equals. We can see that the value of y1 is 1 and the next value is going to be 2. And so when we press equals again, we get the next value, indeed y1 is 2, and now mem is 3, and so on. So we're remembering that value from one cycle to another. Essentially, if the system finds that mem is empty at the beginning of the first cycle, the specification in init is simply copied into the mem field. At the end of the cycle, the result for the next overwrites this specification in mem. Incidentally, the programmer can't type directly into mem, only the system can put specifications into this, either one copied from init or the result from next. Overall then, you put the initial specification for y1 in the init field and the specification for the next value in next. And that's all. The system manages the values otherwise. I think it's important to just run through what's happening again though. So I'm just going to refresh this page, and now you can see just the init specification and the next specification. I'm now going to press IM, which is initiate memories, and you can see then the init value being copied down into mem for that first cycle. So now when we press equals, that 1 becomes the specification and hence the value of y1, and 2 becomes the value or the specification for mem. Then we keep on doing that, and we see it increasing. Pressing initiate memories, or IM, always resets the specification for mem back to that defined in init, as does pressing the start button. So if I press start here, that also sets everything back to where it was and carries out the calculation. So we now have 2 as being the next value for mem. Sometimes we want to use these memory values within the termination conditions of repetitions. So if we say repeat until y1 equals 500, and then we go up here and we press start, we can see that this will continue until we get a value of y1 equal to 500. There we are. Note that during repetitions, results of boxes are not normally displayed, but changes to mem are, as this forms part of the new program. So overall memory boxes are actually calculating 2 values in each cycle. The main value, for example y1 in this case, and the next value, which would be called new y1. However, you can't enter new y1 as a specification in any other box. It will, however, show up. If you did a flow, you would see new y1 showing up. Let's just try that. If I press flow here, we can see that new y1 shows up there. So state is handled in Numipulator through changes to the input specifications, that is, changes to the program handled automatically by the system. Now, memory lists work in exactly the same way as memory numbers, but with 4 list fields rather than 4 number fields. We'll demonstrate these and also some of the other features we've just looked at to implement some dynamic graphics. So let's clear the program and go up and generate 100 zeros as background for our graphics. I'll just put a note in there, black background, that's a comment. And now we'll come down to the table construction U1. So we're going to take G1 here as our input values, 10 as the number of columns, and then we're going to create red stripes by taking this and using fill block values to create some red stripes. So fill block values, I must remember to put the 0 in here for D, and now we'll add in the red stripes, which will be a red stripe starting at row 2, column 1, and we want it to be 3 long, 3 deep, 3 cells deep, 10 cells wide, and we want the color to be -3. And then we'll do the same thing again for the second stripe, 7, 1, 3, 10, -3. So put some notes in here what we're doing. So that's background, and then this is red, and that's also red. We don't need to add these in, but it can be helpful to us if we do so. And we can now go down to the animation zone, make U1 the input, or we'll change its size to 10 and say equals, and there we have our two red stripes. Now we'll go back to row U, and in G2 we will again use G1 as our input and n cols equals 10, and this time we will use edge block values as the function, which will mean we'll just get a square with no fill, and we'll put a 0 in there, and we'll say that the values we want are, we want it to start at row 3 column 3, to be 6 cells deep and 6 cells wide, and we want it to be -5 as the fill, which will be blue, just as a reminder to ourselves. And now we can come down and look at U2. Let's check that's what we've got. Yeah, there we have it. Now we want to get the red stripes moving. So let's go up to Z1 and we'll let that be the current state of the stripes. Now this will start off as U1 and init, so whatever we've got in U1 now, that's it. U1 is the initial value, and the next value is going to be T1, and we'll leave it at that for now. So we need to define what T1 is. So we go up to T1 and we will say that the input for that is the current value of Z1, so that's whatever we're remembering as the current state of that image. Again, 10 value, 10 columns, but we're going to say we want to shift it down. So shift rows down, and now we want to make T1 the input here. Let's make T1 the input here, and we want to have repetitions so that it never stops. So let's say repeat until 1 equals 2. And now let's look what happens when we say start. So at the moment we're still seeing the old blue box. So now we press start. Oh wow, it's a bit fast. Stop. So those, you can see that those stripes are actually scrolling down. You can see visibly that they are scrolling down. So let's add it, make a change up here and make the delay between cycles, I don't know, 0.1 seconds. And we'll do it again. And now you can start to see those red stripes scrolling down. Now we're going to get the blue square moving, and we're going to use T2 and Z2 in the same way that we used T1 and Z1 for the red stripes. So we're going to make Z2 the input here for LA, again 10 columns. And rather than shifting rows down, we're going to shift columns right. We might as well put in here blue right, and this is red down. And just some notes to ourselves. Then if we come down to the bottom here, and I've already put in here U2 as the initial value, T2 as the next, and we can say that is the current blue square. So if we go down further and we've got repeat until here. So now if we make this T2 as the input and press start, we see our blue square moving right. Finally, we can superimpose the square on the stripes using the if then else items function, P1. So if we now say if Z2 is not equal to 0, so remember that's the current value of the list of stripes square, then we use Z2. If not, then we have the value Z1. And now if we go down and change the input down here to P1, and press start, you can see that you've then got the red stripes moving down, the blue square moving horizontally, and with the blue always appearing as though it's on top of the red. I just want to show you now the flow and the values for that program we've just written with the scrolling stripes and the blue square. So if I press on the flow button, you'll see it's quite a simple program. You can see that the animation depends on P1, which is our if then else, which in turn depends on Z2 and Z1, and they in turn depend on U2, U1, G1 in both cases. Then you can see separately we've got new Z1 and new Z2, and we can also see our repeat until and control one. They're not dependent on anything, they're just values we've entered. So that's just to emphasize that these things like Z1 and new Z1 are treated as independent values. We can see that again if we look at the actual values. If I just press equals here and do it again, you can see all those values there, and again you've got next value of Z1 there, and you've got Z1 up there. Now, a point worth noting about the way Numipulator works is that we defined the initial value of Z1 to be, what was it? Let's have a look. U1. Now, U1, which in turn depends on G1, will not be used anymore until the end of that program, even though it will be calculated at every cycle. So in that sense, Numipulator has quite a lot of redundant evaluation. It keeps on generating G1 as 100 black cells and adding stripes to it, but they're not used at all again, because all you're doing after that is remembering the current state of your graphics, and you're manipulating that.